Assalamualaikum warahmatullahi wabarakatuh and welcome to BMMP2543 Material Selection. So before we start with our first lecture, let me ask you a question. Have you ever tried to buy an item through online website like Lazada or Shopee, or maybe you want to go somewhere for a vacation? How do you choose those decisions that you wanted to make? You actually have some decision-making steps that you probably unconsciously did through your mind, okay, thinking about which one you want to buy, which area of vacations that you want to go before you come to that conclusion. So, what are we going to discuss here in this subject is that these decisions also can apply through, so that also applies to when we want to decide what kind of material that we want to use to, let's say, make a product or use in a process. This decision making is really important for the item of a product. This subject seeks to explain and share what are the method or thought process that went through engineers, managers, or even industries deciding on what materials they want to make for a product or even use in a process. It is not just choosing between the cheapest item, okay? There must be some factors that they consider before coming to the final conclusion. So stick around and we'll discuss about it. Okay, so this is the course code BMMP2543. Make sure you are registered correctly with this code, okay, in your make sure that you are registered, okay, with this code, so as to not in the later coming weeks, there'll be some difficulty for you to taking the examination and everything, okay. Anyone who's not registered but looking at this lecture, this video, no problem at all. You can still watch it, okay. You want to have a look before you finally take on the subject, no problem at all. So I'll begin with the introduction to the subject, okay. Okay, so this is the course learning outcome, which is nothing to say and what we expect you to gain once you completed this course. And we have three course learning outcomes or CLOs. The first one is wanting you to relate materials and processing selection in product design and manufacturing. And I'll be testing you cognitively, okay, at difficulty level 4 according to the Bloom taxonomy level. And I mapped it at PO2, which is program outcome, and you can refer to this in your academic handbook. The second course learning outcome or CLO2 is wanting you to produce charts of materials or process but using the Cambridge Educational Software or CES for ranking and screening purposes. And I'll be testing you through your psychomotor or through your actions at difficulty level 3, and I mapped it at PO or program outcome 4, again referring to your academic handbook. And the final CLO, okay, which we want you to construct and analyze materials or process related charts using the Cambridge Educational Software for product justification. And I'll be testing you through your psychomotor or your actions at difficulty level 4, and I mapped it at PO program outcome 5. So you've seen this chart actually in your second semester for engineering materials. And this chart, as you can see, shows the groups of materials available. And this list is non-exhaustive. A lot of materials are being developed today, okay, in the past, than compared to the decades ago. So you see, you're really familiar with metals and alloys that's been used since before our the earlier civilization. We have polymers which are abundantly used today in this day and age. We have elastomers, which one of the materials that helped in revolutionize the industrial revolution, and glasses and ceramics. And in between all these materials, okay, in between them, over here, here, and here, we have hybrids, or what is being popularly known as composites. Okay, and composites are not just, you say, monolithic. We have sandwiches also, okay, that's being stacked together with two materials in between with another material. Okay, and all these materials, metals, polymers, elastomers, glasses, ceramics, all of them have challenges for during manufacturing. Okay, and they have different criteria for the product, whether it's shape, will it be solid or hollow. Of course, a really competitive cost so that it can be competitive in the market. Machinability, can it be machined? Okay, or other types of process that is need to be done afterwards, a secondary process. The environmental impact, whether it can be recycled or can be reused, or we can only discard it. And also finally the mechanical performance, which we take into consideration whether or not that material or that product can withstand its usage until the end of its expected lifetime. Okay, so how does material and process selection relate with each other? So a mechanical design comes with its functional needs, meaning that mechanical design for a car, its functional needs is to take you from point A to point B safely. And the process that is available to it is limited by the material capabilities. For example, a car that is being used in a country with 4 seasons is not the same as the cars being used in the tropics. And what material that we choose affects the processing method and shape that are available or can be attained. So, function, process, and shape dictates the materials and process factors. And these factors, we call them as attributes, which are, for example, physical, mechanical, economic, thermal, electrical, and environmental. So selecting the right relationship for materials process to function is part of the engineering design. And this designing engineering components is usually limited by the materials and process availability. So with new materials, new process coming out, we can have newer designs of products. For example, in new advancements in battery technology, we now have electric sports car manufactured by Tesla. So these are the factors that influence selection of material or process. Some of the issues could include properties, physical or mechanical. Maybe that you want a product to have a higher strength or higher tensile strength, or maybe on cost analysis, the material's availability, or its material life and maintenance, meaning that if a new material has a longer lifetime, so you want to change to that material. Manufacturing considerations, castability or formability, meaning that a newer material can easily be formed or cast into the desired shape. And machinability or coatability, okay, you want to have a new coating for corrosion or corrosion protection, or heat treatment, meaning that the new material can be joined, or heat treatment, meaning that the material needs to be heat treated to change or to modify its properties. Weldability means that its ability to the material to be joined with another material. Failure repeatability means that if the newer material or the previous material is often fail at a certain condition, so you have a newer material that is able to withstand that condition. Repairability, and also environmental issues, ergonomic and safety, meaning that the new material is more safe or more environmentally safe to be used. It has more chemical resistance, and for recycling, of course, materials that are able to be recycled in usage, meaning it can be used again and again without detrimental to its properties. So I have talked about materials, okay, that you've been exposed to during your engineering materials subject. So now we're talking about the categories of process that normally undergo in any kind of product. So there are 4 categories of process. Okay, the first one is called primary shaping, meaning that we take the primary materials, the raw materials that is available, and we shape into the first shape that we want to make prior to making the final shape that you want of the product. Okay, it's called a primary shaping. Okay, it's an example here. It's a kind of injection molding here. So the injection molding takes the raw material in form of granular polymer here, and then inject it into any shape that you want, be it a seed or a bottle through blow molding, for example. So those examples of primary shaping, and even casting is also categorized as primary shaping. Then we move on to the secondary shaping. With, for example, here is machining. So we make from the primary shape, so we machined it into the final shape of our product. Okay, so even casting is a primary shaping. Then after cast, for example, then we shape it, we machine it, mill it into the final shape that we want, to the exact dimension that we want of the design that we have. Okay, so next process is joining. So a product could have different parts to assemble, and joining is a method of joining those different parts to assemble the final product. Okay, one method is through welding, which is physical joining method that we heat up using an intermediate material, and we using that to join different parts or different to make the final assembly. You can if we don't use through physical joining, then either we can use chemical bonding, which is for example like an adhesive we can use to join if the material cannot stand the heat. So we can use chemical bonding, okay, to join the different assemble of the part. So the final category is surface treating. Okay, for example, that the product we want to modify to have a certain attribute that we want. For example, we want it to be the product more corrosion resistant, so we have anti-corrosive material to coat the product, or we want it to be able to resist heat higher, so then we can put in heat resistant material to coat the final product. So I've talked about materials, process. Now moving on to the categories of shape of a product, the materials that we can have. Okay, so there are three categories. Okay, the first is prismatic, second is sheet, and then finally is 3D. Prismatic meaning that a shape, when we cut in half, we can have the shape is symmetrical. Okay, the both side of both side of the parts that being cut is at the same, have the same dimension. So at the same, have the same make half. If we combine again, we can have the same shape again. So we can, as prismatic, we can have a circular product, a circle, okay, or even a sphere. Okay, for non-circular prismatic shape, either in I-beam like this one, or even a square or rectangle or triangle. So those kind of process that generate this kind of shape, either in wire drawing, extrusion, rolling, and shape rolling. For sheet shape, okay, we can have flat or dished. Okay, so flat shape is that as you simply know, that has a certain thickness. Okay, and then it can be bent. Okay, and the shape can be assembled or joined together with another shape. For dish, okay, that has curvature, or it has a cylindrical shape, okay, and has a different features with that cylinder. Okay, and processes that produce this kind of shape, we can have stamping, folding, spinning, and deep drawing. For 3D shapes, okay, we can have shape that are generally, because that generally solid shape, okay, that we can produce through process, as for example as casting. For hollow shape also we can is also categorized as 3D shape. Okay, even though you can see difference in between uh, and for 3D shape we can have either solid shape or hollow shape. Okay, and the shape that in 3D is we can produce through casting, molding, or even powder methods. Okay, so now I'll share about some example of material and process problem, okay, that can arise because of we don't have Now I'll be sharing some examples of material and process problems that arise when we choose poorly, or we don't understand the process entirely. So what are the examples that can arise? For example, like an airplane. Okay, so my previous experience working in an aircraft manufacturing component company. So the wing, okay, is the one that helps to generate lift. Even though that jet engine is actually the one that provides thrust, but to lift the aircraft, you need wings, okay, to generate enough lift to lift the whole aircraft. So it should be enough, its stiffness, strength, and its toughness, and it also should be light. If we don't have those criteria properly, I mean like attributes and properly, then we can have so much problem. If it's not stiff enough, okay, then you can have the aircraft wing could be easily bent, okay, during lifting, okay. And if it's too strong, okay, if it's too strong, then the aircraft can break, okay, with when it exceed the force of the lift can exceed. If it's not that tough, okay, it will not only will it not only can it will be break, but also break in failure, okay, sudden failure without I mean any deformation, without any warning, okay. And if it's heavy, then it cannot even generate lift, but the weight of that wing itself can affect, okay, the for the airplane to even take off, okay. So it has to have that enough I mean balance of properties so that it can meet the so it must have a balance of this property: stiffness, strength, toughness, and density, means referring to its weight, light or heavy, so that it can be, so that the aircraft can even fly. So even if, let's say, if a bearing that you use and we don't use a proper lubricant, okay, then we can have features that the bearing can easily fail, okay, as you see here. I mean like as over time, okay, I mean being used, okay, the, the 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 surface of the bearing in contact with another surface. So then in time, if we don't use a proper lubricant, or I mean to match between these two mating components, then we can easily have a failure in the product. And for this is the most famous, I mean most of people share an example of this famous failure, which is the Titanic, okay. Although there are a lot of factors that contribute to this catastrophe, but one of the I mean contributing major contributing to the disaster is the material failure, meaning that they didn't study, and they didn't understand, I mean when metal alloys I mean behave in a colder environment, meaning that the metal or alloy lost its ductility and becoming more brittle. If you want to do joining, also if you don't set the correct parameter, you don't use the correct I mean like electrode or materials to join, so you can have defects, okay, that we can easily see. And also for casting, okay, if you don't have the correct recipe of the cast to be in casting, then you can easily have defects like porosity and blowholes. Now I will share with you, okay, the evolution, how it went through until modern day of both material and process. So I mean, in the beginning, in prehistoric age, okay, we have materials that our earliest ancestors were exposed to and used. And in metals, in the case of metal, we only have gold, and ceramics they use antlers from deers, bone shell from animals, and then we have a leather also from animals to cover themselves, and also they use stone, okay, for the utensils, okay, early on. And then about 40 almost 50,000 years later, okay, then the metals have increased, so we now know how to use bronze, silver also we're exposed to use copper, okay. That's during the age that we have we underwent the Bronze Age and the Iron Age also. And then we have the ceramics and glasses materials are now, we have concrete. Okay, we have known, like for in the pyramids, they used concrete to make those the big pyramids. And then the natural materials, now we have even lighter materials, for example cork, okay, for the to store, I mean, drinks in the bottles and everything. And then about 1,500 years later, then the same metals are being used, okay, in wrought iron, bronze, and everything. And also we still have the same uh, ceramics and glasses that they're being used, okay. And but also the natural materials also is still the same, okay, we use. But now the application is much wider, even though the materials are the same. But then moving to about 1,500 years later, okay, the same metals are still being used. But now what we now understand using cast iron, okay, we can cast I mean iron to have a better properties that we want, okay. If just not just the previously just bronze, casting bronze or copper, okay. Next, about 400 years later, we added aluminum. Okay, we're now using lighter materials. We're now going towards more advanced applications. We want the materials that have the same strength, okay, but at a lighter density, so we can use it in different and a more advanced application. And then about almost 50 years later, okay, during the World Wars, we have even more plastics now being added. Okay, that previously we only used we only started using about 50 years before, but now we have more here. As you can see, more plastic. We have now started to use even different alloy, lighter alloys like magnesium alloys we have here. And now at the present day, now as you can see, we have even more lighter materials involved. We have even composites coming in. Okay, in this day and age, we have composite using in the aircraft, in cars, and even in recreational items like bicycles and even in sports. So you can see as the development evolution of materials, even though the for about less about 50,000 years, more than 50,000 years prior, all the materials at this about around 10,000 megapascal. So as you can see here, I mean from the prior 50,000 years before, more than 50,000 years before, the strength of materials that we use, okay, around about 1,000 megapascal. But when we close to the present day, now we have materials that reach about 10,000 megapascal. We want our usage, our applications are now more extreme. We want higher strength. At the same time, we want materials that are lighter. Okay, at the extreme light, I mean close to about less than about 10 kilogram per cubic meter. Okay. Next, from materials, now we move on to process. Beginning in the late 18th century, this was the first industrial, we call the first industrial revolution, okay, that our ancestors went through. Okay, the introduction of steam power, locomotive, and everything. And then at that time, we have small industries running about two or about less than 10 workers. And then at the beginning of the 20th century, we started with the second industrial revolution. The assembly line and workers are now more less more coming to hundreds of workers. Okay, and then we have, and then with electricity, previously using just steam, now we're using electricity as now more abundant of usage. And then in the third industrial revolution, then we are now using with robots. Okay, and then even though the workforce is it doesn't increase, but the efficiency has been increased. Okay, and then we have electronics components are being produced. And finally, the in 2010 onwards, the industry now going through the fourth industrial evolution, which some of you may have heard. Now, not only the workers may not be there, but the factories are running by itself using automation, using smart systems, yeah, like cloud systems. I mean that it can be accessed anywhere in the world. You can have access of the production data real time. Okay, and this is what the industry is going towards to. Next, I'll talk about product evolution. What happened with the both when materials and process, evolved. What the effect it has on the product. For example, this is normal is the that we normally see with some house that have is the vacuum cleaner. Okay, in the first vacuum cleaner was manufactured in 1905. It was human powered, it was bulky. You have to like pump the vacuum cleaner itself to have that suction power. It was made entirely from natural materials that were available at the time: wood, canvas, leather, and rubber, and it just reflects the use of those materials in that year. And then 50 years later, then because of the, as you see previously, the evolution of the process, newer materials coming like plastics, and then newer process that can be with machines that involve, then we have into a more cylindrical cleaner. Okay, not just a bulky shape of a square or rectangle. Then it's electrically powered. You can plug in because electricity now is abundantly available. It's made entirely of metal. Okay, that can be that more can withstand the higher vacuum power and vacuum from the motor. It is small but it's still heavy because of using metal. And the newer latest that you've seen in the because of as you know from the material evolution, we have now plastics and process that uses automation and everything. So then we have like this robot vacuum cleaners. It's lighter, it's made of plastic, and then the motor is more efficient. It can operate in higher temperature. You can bring it is more mobile. You can bring it. It's portable. You can bring it anywhere you want. So this you can see the evolution. Starting from the about just about 100 years prior, and how we can see the changes in present. And then I show you an example how material and process that relate. What are the products that relate with material and process? Okay, for example, in mechanical engineering, for example, the semi truck, okay, that carries load. You have the carrier to put load here is metal. That we need, that has to have higher strength and higher that can withstand the higher load of the materials that they're bringing to the site. And the gears are made of polymers. Okay, these are the gears because polymers can withstand repeated cycle of usage. The spark plug, okay, that they use to generate combustion, okay, it's made of ceramic. And for sports recreational use, okay, bicycle, okay, all this are using the frame is composite, made from a magnesium based composite metal matrix composites. And then the handle even is composite. Okay, so lighter than we have a better performance during cycling. In aerospace and motorsport, we have the turbine engine. It's made of metal, single crystal metal that is being produced, okay, through controlled environment. Then we have the dynamo that even in that gene. And for dynamo, okay, that produces the energy. So it's made from the cover is made from polymers and elastomers. For the bearings, it's made from ceramic glasses. Okay, it looks as if it's metal, but it's ceramics. And for extreme uh, condition like a jet fighter, it's made of composites, so that it has higher strength, but it still has enough stiffness and toughness to withstand the condition. It can withstand very high temperature, very extreme condition. In civil engineering, okay, we can see the metal frames, okay, of a window, the even the cover of this building, this famous building. And for polymers, elastomers, this is the famous building in Leicester in UK. So this entire cover here is made of polymer. Okay, and for ceramic glasses, of course, we use it as the windows. And hybrid composites for decorative, showing shape here that we have. It's actually, it looks like a brick, but it's hybrid, hybrids and composite material. In bioengineering, metal alloys, for example, to replace kneecap, okay, and polymers, elastomers, materials also, and ceramic glasses too, for replacing bone, for example, using an hydroxyapatite, and for wood shape uh, products that we use hybrids, composites, sawdust, mixture of sawdust and different materials to make to make the product. And for product and industrial design, metals for boiling water to make coffee, polymers and elastomeric to make toys, okay, Lego toys, ceramic glasses to make water bottles, okay, and for drinking, and using hybrids and composites for producing different industrial design, concept cars, concept vehicles that we want. So the software that we'll be using for this subject and course is the CS EduPack 2013, okay, by Cambridge Education Software. So the CS EduPack consists of the CS software, which we'll share with you, that you can install in your own personal computer. Also, you can access to 23 PowerPoint lectures. Okay, you can have look at even some of the slides that I use also refer to this. Next are white papers or case studies of how they use CS software in trying to solve engineering or materials solutions to find. And all these teaching resources you can access at teaching.grantadesign.com. Okay, so you have to understand that this, as I shown earlier, that the CS EduPack is version in 2013, so about 7 years, and also because of the expired license that we only have to access the open source resources in the website. So there are resources that only that the latest license we have, but the rest, those are still open source. You can still access anytime you want to do some tutorial or to do some exercise from the website. And these are the textbooks that I refer to. The elementary text mean the basic knowledge about materials. So this is available in our library, about 2 copies, if I'm not mistaken, 2 physical copies. Next, talking about environment topics in our course, you can also find in this using these textbooks, materials and the environment, which also available 2 physical copies in our library. And also we have for more advanced uh, topics that involve even calculations or some advanced problems and materials selection or process selection. I refer to these textbooks, material selection in mechanical design, also available in our library. I think we have about 2 copies, physical copies also. And finally, industrial design. We'll talk about how materials and industrial design come together, engineering design come together. So you can also refer to this textbook. Also, I think I believe about 1 copy we have. So even though with the limited physical copies of all these textbooks, you have to share with each other. So you don't anyone trying to keep it to themselves. Okay, you have to share with your friends. Thank you very much for staying until the end. Okay, so I hope you gained some perspective on what this course is about. And those even not taking this course, thank you again for staying. And if you have any questions or you want to, you can comment in the video, or you can text me. Okay, the ones that have my contact details, you can contact me directly. Also, I hope you can subscribe and like the channel, okay, because I will upload our all of our course materials in YouTube that involves some explanation, okay, and also the rest you can still our main referral will be still in our uLearn page. So thank you very much and have a good day.